The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we've initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is 10 gold standard architectural learning to build full-stack internet-scale applications. Our guest speaker today is Kapil Sharma. He's a Senior Manager Software Development with PayPal. Kapil is an engineering leader who specializes in developing end-to-end digital payment processing experiences. He currently works for PayPal India in the risk recoveries and protection domain. Earlier, Kapil spent nearly 11 plus years experience in California working for several Bay Area companies such as Visa, Intuit, and Symantec, where he led engineering teams to deliver SaaS solutions ranging from recurring subscription platforms to QuickBooks accounting to consumer internet security software. Kapil is an MBA graduate from Santa Clara University, California, and studied computer science at Johns Hopkins University, Maryland, and Thapar University, Punjab. So without further delay, I introduce you all to our guest speaker today. Over to you, Kapil.
Hi everyone, sorry for the delay. Good morning, good afternoon, good evening, depending on where you are located right now. This is Kapil, and I'm going to walk you through 10 architecture principles spread across the full stack that will help you build scalable web applications. So let's jump onto the presentation straight away. So this is at a high level the agenda for this session. My objective is to make you appreciate different nuances across all the tiers in terms of understanding patterns to build scalable applications. And we will cover some principles on browser layer, some principles on web and application layer, some principles on messaging layer, and then the data layer, and then my favorite one, the forgotten layer, which is essentially the monitoring of your SOA application architecture, which normally fell through the cracks until late in the game. All right. So let's go to the browser layer. So this is the first principle, which is sort of a low-hanging fruit because it's so easy to do it. However, a lot of web teams essentially don't pay too much attention to it upfront, which is leveraging the browser cache, essentially the client-side caching. So it's obvious that if you cache a resource locally on the client side, it's going to really decrease the load on your servers because you will not get requests for resources that are not stale on the local client, right? And obviously, on the other side, user is going to have a better experience because page or the web resources are going to get loaded faster. So what are some of the key HTTP headers or attributes that you could use to pretty much enable the caching and optimize it for the client, right? So the key one is expires, which allows you on the server side to set a timestamp for some of your web resources to let the client know that, hey, you know what, this is a timestamp set in future that you can use to guide yourself not to get calls to get the resource because the resource is not going to get stale. So it allows you to optimize the client-side experience in such a way that your web browser will not actually even make get calls at all, right? So that's what some of the modern browsers do. Similarly, there's a HTTP header called cache control, which is attributes like max age. Pretty much solves the same purpose, allows you to set in seconds the time window for which the resource can, stay as cache resource on the client side without needing a fresh pull. Another important aspect of cache control is a header attribute called public. I normally encourage you to set this attribute if you are dealing with non-sensitive resources that can be cached in the intermediate layers like proxy servers or CDN servers. It allows you to get to resource faster, especially in use cases where your client browser caches have been purged or they are actually disabled. And finally, last modified. I'm pretty sure many of you must be familiar with this. It's a weak form of browser caching control because it actually allows to make only conditional gets. What that means is, let's say client is pulling a resource and it's a hard pull, which means the resource is actually getting downloaded for the first time on the client. There's the last modified timestamp that you can configure on the Apache web server, for example, that guides the client that, hey, next time you need the resource, you can make a conditional get request by including a timestamp called if last or if since modified. We'll see an example of that, and that allows you to pull the resource only if needed. You still make a hop to the web server, but your web server might be just returning 3 or 4 because the resource on the server side is pretty much the same that you have on the client side based on the timestamp, right? So let's look at an example. So this is an example from a get pull request that I issued for my LinkedIn account. So this is a get call for pulling my profile picture. If you look at response headers, you will see that you have expires, which is set to 2nd March, which was actually exactly a week from when I made this request. So essentially, I, on the local client, can keep pulling this resource until 2nd March without actually making a get request. So many web browsers are smart enough to not even issue a get in this case. Similarly, you can see cache control max age, which is exactly same as the guidance timestamp in expires, which is 604800, which is actually 7 days, right? So essentially it plays the same role as expires timestamp. And then you can see in the request header you have if modified since that the client had set, and that timestamp reflects the last time the resource was pulled by the client and the copy timestamp that it issues to the server for this pull. So this is a classic example of things happening the right way. LinkedIn is doing a good job in making sure that it gives the right directives to the client to be able to optimize the caching on the local node. Great. So let's move on to the next principle on the browser layer or the client layer. And that principle is use CDN. So CDN essentially is content delivery network, and it's a sort of distributed clustered architecture where you have certain service providers like Akamai or Amazon who have edge nodes geographically distributed across the world that can serve static content to your customers much faster because of the reduction in network latency. So CDN allows a company or an enterprise to deploy static resources on a geographically distributed set of edge nodes that can be served to your customers in a much smaller time window. So some of the questions that normally people ask, to figure out whether to use CDN or not are the following. And these are pretty much common sense sort of questions, right? So first is, do you want to reduce traffic to your servers? Obviously, why not? If the CDN edge nodes can take that traffic up and serve the content, your servers are better off that way. Do you want faster page loads? Obviously, I do. Do you want to improve conversion? And studies have been done to prove that, small differences of 1 second of reduction in latency can improve conversion by double digits. So why not? And then normally what happens is you work with a content delivery network to pretty much push or replicate your static resources to the edge nodes. And the way it works is pretty straightforward. So when your client issues a get, it actually basically hits the edge node on the CDN network first because of the CNAME alias that kind of matches with the actual physical origin server, right? So it hits the CDN. If the CDN doesn't have the cached version, because it is probably the first ever pull from any client for that resource, it would actually hit the origin server, which is your own server deployed in your data center, to pull the resource. And it's going to cache it on the edge node, which is geographically much closer to the customer than your origin server. And any subsequent request from this client or any client in that geographical geographical location is going to get the resource from the edge server next time, which is going to reduce the latency. So clearly, you are going to delight your customers by reducing the load time. One reason many companies don't do this today is because of the cost reasons. It's sometimes very expensive depending on the traffic that you are serving to deploy and leverage CDN services. But a lot of small niche players have shown up lately, which are giving you very good bang for your buck to leverage their CDN networks, and you should certainly explore them. So great. This is the second principle we just covered. Now let's move on to the next one. So we'll talk about some principles on the web application layer, and some technical geeky folks can, kind of relate this to your Apache web server or your Tomcat sort of containers, right? So aim for statelessness. This is our third principle, and we are essentially moving, from presentation tier to middle tier now, or the web tier now, right? So statelessness, is a very, sort of very, very, very important principle that you should stick to, when designing SOA architectures, because affinity always reduces scalability. What that means is, if you're managing state of your clients on the server side, it's going to really create problems for you. Problems like, you need more memory to do that state management. Your code is going to get more complex on the server side, right? And more importantly, and most importantly maybe, and this is what I have seen in practice, you have to have operations configure your load balancers in such a way that the load balancer is session aware, which means that if I'm an end user and I'm hitting your node A, right, and my subsequent request, which requires state from the previous request, is going to node B, right, then that's not going to work out. So you need to have a load balancer that routes your second request to node A, right, because that's the node which knows the state. The other way to solve the same problem that I've seen, which hasn't worked very well because of operational inefficiency, is session replication, where, okay, you know what, you can go to node B because you want to fairly load your load balancers, but you need to replicate the state across containers because node B doesn't know anything about state in node A. So unless you replicate, you will not be able to serve that customer for the subsequent request. And this can become very expensive because operationally it's a challenge to do this. So would you rather spend time writing the business logic and spending more time on your core capabilities, or are you going to mess up with the operational aspects of serving your customers? Probably the former, right? However, having said that, there are use cases and compelling use cases where you want to maintain state. And our recommendation is, and my recommendation is, to try to delegate the state management to the client. So if client, especially the model view controller sort of clients, right, rich clients who are using Backbone or Angular or other MVC frameworks, if they can manage the state and essentially send the state in the subsequent request to the server, great. You don't need to manage state on the server side. That all you do probably is look up additional data based on the stickiness handles that client has sent over to you. So that's the best option, normally that you should strive for. And obviously, sometimes there will be situations where you want to manage state on the server side because you have a SOA decouple sort of architecture, and some of the pieces of your SOA architecture have made certain decisions about, a client request that other components of your SOA architecture need, right? Like, for example, if you have service A and service B, and service A has made certain decisions which will be used by service B for the subsequent request from the same client, you need to make that decision or a state available to your service B to be able to accurately do what the request is all about. So in that case, you do end up using some sort of distributed object cache for state management. But more important point here is that you are still not doing state management on your powerhouses or your application containers and web server. You are delegating it to a centralized object cache sort of topology, right, which does it for you. So that makes sure that your web servers, application servers are lightly loaded in terms of state management. Okay, so let's move on to the next one. So this is the fourth principle, and the principle is use async endpoints to improve transactions per second or throughput, right? So, when you are serving traffic, you want to make sure that you can serve as much traffic as you want, infinite traffic, right? And that's the whole point of being a scalable system, right? Which means that the access point to your ecosystem of, your services should be able to take a lot of traffic without really getting bogged down. So if you have certain use cases where, you know that they are IO intensive, right? Then you want to probably go with async endpoints so that you can take that request, put it somewhere, maybe in a message queue, maybe as a request in the database, right? And then take it up, offline using some worker threads or some sort of async strategy that you might have for your system, and then make the results available to the client when and as they are available. So that ensures that the request that just came in, right, which was served off of a thread in the thread pool of the container, can actually get offloaded, and that thread can serve the next request. So essentially it increases the scalability of the pool of connections you have that's serving the traffic from the external world. And it certainly improves responsiveness, right, because your client is pretty much happy doing something else while you are doing the grunt work for him. So based on the use cases, adopting async endpoints on the service layer is going to really scale your system very well. And some of the classic examples are on Facebook platform. You have async endpoints that allows you to create ads in bulk. Very, very popular example. A word of caution though that, async doesn't mean that you can build a async endpoint in such a way that you are still sort of spawning a worker thread immediately and doing the grunt work and returning, from the client perspective, but still keeping your critical resources busy all the time. So try to implement a true async behavior where you are truly offloading the work to a pool of worker threads that you might be maintaining as part of your back-end processing. That's the ideal way to do async. All right, so let's move on to the next principle, which is embrace server-side caching to scale data tiers. And a lot of companies actually do this very well, right? However, there are companies that I've seen which believe that, SOA means we are inherently scalable, so why do we need caching? But caching solves a different purpose, right? So caching makes access faster. It gives user a much better response time as opposed to with no caching, right? And obviously it depends on use cases as well. We will touch upon some of those use cases as we go further. But it's very common to use caching layer on the server side such that it's a combination of a near and distributed cache. So what does it mean? So near cache essentially means that you have some small footprint of memory available in the local node that your client application is running on that can get you objects or user objects much faster because it's in JVM, it's on heap, right? So you're going to get a very fast access to an object that you need. Distributed cache complements near cache. So what it does is it actually gives you ability to either pull an object from the disk, maybe on the same local machine, or it's going to go to the cluster of cache nodes that you have as part of your larger caching strategy. And we'll look at a diagram in a second to understand what that means. But before we go there, an important call out about replicated cache, which is different from near cache and distributed cache. So near cache was, as I said, mostly about keeping a small set of objects which are very frequently accessed in JVM on heap, right? Distributed cache is more about you have, let's say, 10 objects. You distribute these 10 objects across the cluster of, application server nodes that you have, such that no single node has, two objects or, same copy, right? And then replicated caches, you have, let's say you have 10 objects. You have all the 10 objects on each node available to your client, which means you don't have to do hops to get to those objects, right? So normally replicated cache, which means that you have all the objects that you need available, on the same node where your client or where your server-side application is running, is usually used when you want a zero latency access, because you're not doing any hops. Everything is right there and then, but it needs very, very sophisticated machines for you to be able to do that, right? So let's actually look at one of the topologies, which is sort of most popular topology, which is a combination of near and distributed cache. So, as I explained, look at JVM1, the first box, right? So you have an application on the server side running, which requires an object named B, right? So as you can see, B is not present in the JVM1. It's not available in the partition cache, which is similar or synonym to distributed cache. So if B is not available on JVM1, then it has to do a hop. The caching infrastructure will take care of it. It will have to do a hop, go to the node where B is actually resident, which is JVM2 in this case, right? And get that object in the partition cache or the distributed cache running in JVM1, which is normally sort of, for example, big memory in the case of Terracotta, right? And then when B gets pulled by the application, it stays in the local cache as well, because that's going to give you the most efficiency, right? Because that's in heap, that's on heap, whereas partition cache is off heap, right? So this basically gives you an idea that you can essentially get to the objects faster, by having some sort of combination of near and distributed cache, which gives you the best of both worlds. So if you have a lot of requests for the same object over and over, having a local cache is going to really help you, because you just pull that object from heap. However, if you have needs to pull objects from distributed cluster, because maybe you have huge set of cached objects, right? You have a huge population of end objects that you need for your use cases, then you go and do hops and fetch that object. So to wrap up this principle, looking at near plus distributed cache combination is certainly going to help you if you have the infrastructure to do this. Okay, let's move on to the next principle, and we will address this principle under messaging layer. Use messaging queue to decouple integration heavy systems. So, SOA is all about decoupled systems, right? So how do you achieve decoupling? Well, obviously we have talked about creating very fine-grained services and, interacting with services and so on and so forth using point-to-point calls. But if you have so many fine-grained services, right, and more importantly, if you have integration-heavy architecture where you need to feed data from one service to another and so on and so forth, you need to have a much more scalable infrastructure to do it, and messaging queue allows you to do that. And these are some of the questions I usually ask people before I tell them that whether you need a messaging queue or not, right? So do you like decoupled systems? Obviously you do. Do you have a lot of consumers of a data that's produced by one of the components of your SOA architecture? Do you have more than 2 consumers? Yes. Do your consumers prefer near real-time processing, right? So which means that an event is available. Would your consumers want to consume that in almost near real time? Or can they wait until the end of the day so that you can batch process them and make the data available to your consumers? Well, if the answer is yes, your consumers do prefer near real time, then great. Messaging queue really solves that problem. Is losing messages deal breaker for you or for your most important customers? Well, if yes, then messaging queue is great because it gives you durability, right? I mean, you can persist these messages using MQ or messaging queue infrastructure as the backbone. And then, even if your consumers are down and out and they're getting rebooted or whatever, right? You can still make the data available to them when they are back up. And finally, do you have a mix of slow and fast consumers? Do you have consumers who absorb this data at their own speed, right? Well, if yes, then messaging queue is a great option because it allows throttling, right? So you can pretty much consume data or produce data at your own pace. You can customize that. It's a little hard to do because it's very configuration intensive, and more configuration means more moving parts, but certainly it's possible. Okay, so messaging queue certainly gives you a great way to decouple a very integration heavy architecture. One pitfall I have personally seen of using message queue is a lot of components in your huge integration heavy ecosystem, right? They start saving the data in their own databases in silo, which is not a good idea, right? Because sometimes you just need data to make certain decisions, or maybe to send an email or whatever you want to do upfront, and then you don't want to persist that data, right? You can always pull that data later using a web service call from the system of record, right? So I think that's the practice that I normally encourage, that as a consumer you can pull data from message bus, from the messaging queue, but don't store that data in your local database if you don't need to, because then at some point of time if the data gets stale, from the system of record perspective, you are gonna be in trouble, because you are probably not gonna listen for that change, and then you're gonna have a stale version of that data down the line, which is gonna come and bite you back, right? So try to pretty much weigh the pros and cons, and then design your consumers and producers in such a way that you are not caching local copies of the data that you can always pull through get calls. Great. So the next principle that we're going to talk about is sort of natural progression of the previous principle, which is be selective when publishing on the message queue or the bus, right? So, well, great, you have a message queue now. Would you want to put everything on the bus? I mean, integration heavy architecture doesn't really mean that you can just use message bus for everything and anything for data sharing, right? There will be certain use cases for which you should do point-to-point calls, right? You can always do get, as long as you have handle to what resource you want to pull, right? So this principle focuses on the fact that, hey, you know what, messaging bus gives you scalability and decoupling, great, but it has costs associated with it, right? So as you're gonna put more data on the bus, your cost of maintenance for that message queue on the bus is gonna go up as well. Think about it. Message queue gives you federation layer to sort of transmit messages from producers to consumers, right? It gives you durability, which means it has persistence units that it's going to manage. As the data grows, there'll be more pressure to sort of scale out the persistence units, or the database tier of the messaging queue infrastructure. And it has so many moving parts essentially that as the data load increases, it's going to really put pressure to maintain that MQ infrastructure or messaging queue infrastructure. So what I mean to say is that bus doesn't mean that you have to use it for everything. Be selective. Not all data has equal value to the business. So be very selective and decide which events you want to publish to the bus, right? And even more importantly, when you're publishing an event, what payload do you want to associate with that event? Do you want to put the full payload, the full resource, for that particular event on the bus, or do you want to just put a handle to a resource tied to that event, so that consumer knows that there is a change, there is a state change, or some data change, and if they need to, they can pull the additional details about that resource using the handle you have pretty much dropped on the bus. You don't have to put the whole payload on the bus. Just put the bare minimum that your consumers need. It's always a challenge to make that decision, but do spend that extra time to figure it out. Don't just drop everything on the bus. That's going to make the life of MQ or infrastructure guys much easier than otherwise. All right? Okay, so let's move on to the next set of principles, and these principles will talk about some of the storage, some of the database related scalability patterns, and we will spend a little bit of time on a couple of these principles. Okay, use NoSQL to scale writes for big unstructured data. So NoSQL popularity is certainly going up, right? Look at Facebook, look at Twitter. They are serving so many requests, right? I mean, billion requests a month for Twitter. Millions of, posts, happening on Facebook on a given day. I mean, that's a lot of unstructured data, right? So, you should ask yourself some questions when you're designing your data models, or, you're trying to solve, some business use cases. Do you have unstructured data? A tweet is a classic example of unstructured data, or Facebook post is a classic example of unstructured data. I would say even user profile, could be considered as a semi-structured or unstructured data, because profile attributes could grow, right? So do you have unstructured data? Does your schema change every now and then, at least every few months? And a lot of, kind of churn because of that. Do you like to have built-in scale out, do you want to use commodity hardware to build scale out, database tier, right? That would scale your write really well, right? Do you prefer integrated caching layer, right? A lot of the NoSQL databases today come with integrated caching layer. Cassandra is a classic example, right? Why would I not want a database tier or a data tier that has caching built in? It has less moving parts, so I don't have to worry about setting up a caching layer and integrating with it from the application layer perspective. I'll never have a cold state, because if my caching layer and data tier are going hand in hand, then every time there's a situation where, let's say, my node is booted up, my tier is going to take care of, loading the cache as opposed to giving me an empty cache next time, right? And then it's going to match my database tier. If small footprint of data set that's being managed on that node is going to fill up the cache, assuming you have enough RAM on that node, and it's great. I mean, there'll be not a situation where, I have a stale data in my cache, because it's sort of tightly integrated. Do you like built-in fault tolerance, right? Who does not? I mean, I want availability. If one node goes down or two nodes go down, I have a symmetric sort of ring architecture in Cassandra where any node can do reads or writes, right? There is no master-slave sort of notion attached to them. So great, my availability seriously goes up. And I think even MongoDB, who used to traditionally have master-slave sort of topology, is coming up with, a little bit more symmetric sort of topology, right? And more importantly, would eventual consistency suffice? I mean, is it okay for you to, read data that is not accurate at that point in time? Maybe you are doing a read from a node that doesn't have the updated version of the data change yet. So is it okay for you, right? If it's okay, then wow, man, I'm going to use NoSQL. Why not, right? So, and the way the NoSQL works in principle, for example, let's take Cassandra, right? How does it make writes faster for you? Well, one of the things it does is it actually does a write in memory, right? So it, if some of you have worked on Cassandra, it has this concept of memtables, right? Which is an in-memory sort of space that writes go to, right? And only after a certain period of time it flushes that data to the disk, right? So imagine, I mean, you're doing writes on or in memory as opposed to on disk. Obviously, man, you're saving on I/O time, which is gonna make your writes faster, right? And then normally what topology like Cassandra has is they have two sort of layers of cache structures. Like I think they call it a row cache and probably keyed cache. So row cache is a much smaller in-memory sort of space available to cache the entire set of rows, for the clients to be able to query and get. Whereas keyed cache has a much larger footprint, but it only caches the keys that can be used to look up the data either in the mem tables or on the disk. So I'm not an expert on Cassandra, but that's how it sort of at a high level operates. So in-memory writes really give you the biggest bang for the buck in terms of scaling your writes, right? And then, there are things like auto sharding and whatnot that are essentially out of the box with NoSQL topologies. So you don't have to worry about sharding on your own and things of that nature. Great. So use NoSQL to write for big unstructured data, and that's really an important principle that you should keep in mind. All right, let's move on to the next principle, which is on sharding. So sharding, I love it personally. I haven't done it, but I've seen a lot of teams doing it in the organizations I've worked for. It really helps if you do it right, if you have the right reasons to do it, but it's very hard. It's really hard. Certainly it's very useful because you can use low-end commodity machines to scale out your data sets. You know, you have lower latencies because you have smaller data sets that you are running queries against, but it's hard, right? Especially if your data has a lot of relationship and aggregation sort of queries built in. So picking the right shard key is very hard as well, right? And one of the reasons I've seen that is true is normally 10 to 20% of your customers are the most demanding, right? So how do you pick the key in such a way that traffic from this small pool of customers are fairly balanced across your nodes? It's always a hard thing to do, right? And as I said, if you have queries that need some sort of nitpicking from different shards, right, where you have to do cross-site queries, bring the data, and then collate either at the application layer or some sort of abstraction between application data tier, your performance might actually go down, right? So it's not easy. And finally, I mean, application layer could become complex because I've seen teams writing shard lookup logic, obviously not in your business logic code, which is pretty much a bad thing to do, but some sort of abstraction between application and data tier to actually figure out which is the right shard for the query to go to. It becomes really hard to maintain that sort of code. And my favorite, more or less, is it's operationally challenging, right? To have sort of sharding infrastructure when you have to add an index or chain schema. You have to now deal with different shards who sort of host that schema versus, a single or couple of boxes that are running your relational databases. It becomes challenging to do this in one shot. Normally the way people do it is they take some shards off the heap. Of the the system. Obviously, they have replicas, right? Do it for those shards and then bring them back on and do it for the next set and so on and so forth. But it's kind of challenging. So the crux of this principle is sharding is not bad. You should certainly do it if you have to, but certainly make effort to look for simpler solutions, right? Sharding is cool, great, it's a geeky stuff, but do you really need it? Can you just archive, your last 4 years of data and just keep this year of data to serve or maybe 90% of your use cases, right? If you can, then maybe you can do away with 4 years of data and then just keep only the current year of data that you need for serving most of your use cases. That's going to reduce the footprint of your data sets and that's going to make your queries really fast, right? Why not? Do think about it. And then partition by function, right? This is another thing that you could do to first figure out if, let's say you have a database server, with a database that has 20 tables, right? And let's say 10 of those tables are taking most of the traffic. Could you separate out some of these tables, maybe out of these 10, maybe functionally you can split these 10 into 5 and 5, maybe 5 serving a particular subdomain and 5 another subdomain, if it makes sense, right? And move the set of 5 to another machine, a dedicated database server. So essentially you are dropping the traffic on your current database server that's hosting all these 10 tables by 50%. If you can do that, and if it makes sense architecturally to partition by function, why not? You can avoid sharding in such cases, right? So it's important to think about simpler solutions first. And finally, our last principle, probably the most, the most forgotten one, and it's one of the most important principles in my opinion, which is that you have this huge system, a very well-designed SOA architecture based system, right? You have very solid design with loosely coupled services and components. Across your tiers, you have very fine-grained sort of, responsibility. But what's the point of having the system if you can't really monitor whether you are actually serving all the business use cases in a way you should, and more importantly, do you have way to figure out if there are scalability bottlenecks in your SOA system, right? So that's where application monitoring plays a huge role. It should be a first-class citizen, in this loosely coupled architecture where scalability was and availability was, right, your main concern. Do you have a way to have an end-to-end view of your business transaction if you need to kind of troubleshoot or monitor things across the layers, right? Do you have a way to do it? SOA certainly makes it harder, right? So you have possibility of having bottlenecks in any of the layers we talked about, your application containers, your JVMs, your message queues, your database tier, right? Your NoSQL layer, right? So how do you make sure that you feel good about the fact that you can even monitor the end-to-end flows without really losing your sleep, right? So that's why I pay a lot of attention to this principle, which talks about, please make sure you think about monitoring upfront as opposed to an afterthought, right? And, one of the things I've personally seen is that clients are getting very thick, right? A lot of business logic is moving to clients, especially with single app frameworks like Backbone or Angular, right? There's a lot of logic on the client side with very little instrumentation to actually figure out if something is wrong, then, how can I trace the root problem on the client side? So that's why front-end layer instrumentation is very important, right? So you could instrument your front-end code in such a way that you could send some sort of, data, maybe to an async AJAX sort of calls to your server side, which is sort of logging some of this data, that's originating from the front-end layer for monitoring purposes, for troubleshooting, for doing deep dives. Certainly don't put this as an afterthought if you have thick clients. You have to instrument your front-end layer to be able to troubleshoot issues quicker and accurately. Make sure on the server side as well you have hooks before and after transaction. You log, publish, and then monitor. And most importantly, you should have business metrics to figure out if things are going the way they should, right? I mean, just sort of logging an exception doesn't mean anything to me, right? There has to be business metric associated with everything you want to monitor. For an example, right, we deal with a lot of collections related use cases where, if users' accounts have money less than certain thresholds, we want to send an email out to the user or set of users saying, hey, you know what, you need to put additional money in your wallet, right? So, I should have some sort of trend and threshold sort of things in mind to be able to monitor whether, I'm pretty much, in line with the threshold I've set for this use case, so that I can say that, hey, you know what, my architecture, my end-to-end flow for sending an email for a user who has low balance is sane, is doing well, right? So make sure you work with your product guys to put business metrics on plate to be able to rationalize your use cases. And there are a lot of tools out in the market like App Dynamics. There's another tool, a very cool one by New Relic, Keynote, Nagios. I mean, there are a lot of tools out there which gives you out-of-box, infrastructure to do monitoring. They can pull data from various data sources that you might have, and in fact, they can help you instrument your front-end code to be able to send data to some sort of infrastructure layer at the back end, and then paint some dashboard views or trend views for you to be able to rationalize the functional aspects of your use cases. So don't, postpone the monitoring aspects. Make it an integral part of your scalability discussions, your availability discussions, and, do this religiously. And that's the last principle we wanted to discuss. So with that, I'm done with all the 10 principles. My intent, my objective to do this was to make you guys appreciate that, just profiling one tier, more commonly data tier is not going to give you the scalability you want. You have to profile the full stack. You have to look at various scalability, optimizations or various aspects of, achieving scalability across all tiers from front end all the way to the data tier. And if you don't do that, at some point of time, it's going to come and bite you back. So certainly pay attention to the full stack and make solid scalable applications that scale at the web level. Thank you guys, and I'm going to now ask the moderators to open this up for any Q&A. Thank you.
Thank you, Kapil. Thanks for this insightful presentation. Let's quickly take up the questions now. I would request you to read them out and give their answers so that all our users may listen to your commendable insights.
Sure. Okay, so we have one question which says, is CDN one kind of caching? It provides caching of images. Is there any other advantage of CDN in addition to move content near to the client side for lower latency? Well, it's not only caching of images. You can cache any static resources, be it images, be it video files, audio files. In fact, you know what, I have seen companies caching resources which are not truly static in nature but can be pre-computed and deployed on CDN networks. So, you know, if you know certain things that you can pre-compute and deploy maybe as part of the static content that you would serve to the clients, you could do that too. And the second aspect of the question is there any advantage of CDN in addition to moving content near to the client for lower latency? You know, it's not only about moving the content near to the client. Certainly that's the primary objective, but CDN allows you to actually deploy some custom routing logic if you need to scale better. For example, I've seen companies who work with the CDN providers to route traffic not necessarily to the nearest location to the client, but to the least busy servers they have across the world. So it's not just about the geographical location, it's also about fairly balancing your server-side infrastructure. And there are a lot of other value-added services that CDN providers can do. They can do compression and whatnot for you. I mean, I would recommend you go to, you know, Akamai website or Amazon CloudFront website to learn more about some of the value-added systems or services that these guys provide. Thank you. All right, let me move on to the next question. Okay, this is a little long one, so let me try to read it all the way through. So this question, I'll read it out as I read. I'll read it out as I go through this. So we are using decoupling in my application by making REST calls among different applications, different components. Great. The only challenge we face is, in some cases, there are multiple hops, such as A calls B for some data and B may call C. Sometimes C may need to consume API of A to reply. So there are multiple internal calls, and due to that, number of connections does increase on the database. Any best practice there? Well, you know, it sounds like your database is becoming a bottleneck. So if that is your main concern, I would certainly look at some of the principles we discussed, like you know, partitioning by function. You know, make sure that if you are, you know, if you have several data models serving different subdomains, you don't host them in the same database, right? You could essentially partition the tables by function and, let's say, move your wallet-related tables to one database. You can move your subscription-related tables to another database. You could move your fraud-related tables to fraud database, right? So you could do that so that load on your database is essentially scaled out. Right, and then we have discussed about sharding and other principles, and more importantly, we have discussed about messaging queues. So if you have multiple components, like you just talked about A, B, and C, which needs to do data sharing, could they leverage message queues so that one guy can drop the data and the other guy consumes it? This would obviate the need to essentially do a point-to-point calls across the jungle of components you have. So, you know, you can go through these principles and that I discussed, and then probably pick and choose some of the principles that are applicable to your use case. Thank you. All right, let me try to go through some additional questions. There's a very good question which asks about session management. So it says, for online transactions, session management is a must. How can we do that at client level? Absolutely. You know, if you are maintaining some user authentication, authorization related information, you know, you have to keep some small sort of footprint of the state in the session on the server side, which is fine. The state management I was mostly talking about was about, some of the business data model related state, attributes. Like, for example, if you have a 4-page, application where you go from one step to another, and let's say step 3 depends on some data or some settings you had chosen in step 2, right? Do you really need to keep the settings that you just, selected in step 2 on your server side? No, you can just keep it in a model on the client side, and when the user goes from step 2 to 3, the state or the setting state can actually be sent from client to server. So server doesn't need to do anything, right? So that is the primary, use case in terms of not managing state on the server side. Thank you. There is another question, a very good one, which says, what are the best way to resolve the server sticky session in distributed environment? I've seen this problem a lot in some of the previous works that some of the teams did. Server sticky session, it's very operationally challenging to do that. You could certainly tweak your load balancer configurations to be able to create notion of sticky sessions so that, your load balancer is session aware and they route the calls to the same nodes that the previous request went to. So there is no, as such a best practice, it's very customized according to the sort of web server infrastructure you're dealing with, the load balancer infrastructure you're dealing with. So I think it's gonna be going by the book and making sure you do the right thing for that sort of topology that you have. Okay. There is another question which talks about in microservice architecture, we have decoupled components. Great. How to manage transactions, REST calls, HTTP requests between every component. So this sounds like a very open-ended question. I think sounds like you have a system where there's a lot of back and forth, point-to-point calls across components. And that's sort of creating a lot of mess for you because obviously you need a, system where everyone knows everyone else, right? My suggestion is certainly look at, possibilities like messaging to infrastructure, which can obviate the need for intimately knowing all the components in the ecosystem of SOA world you have. Rather, you or your components essentially rely on the topics that are published to essentially consume data, right? So that will make life much easier in the sense that you are going to move away from tightly coupled system where everyone knows everyone else to a loosely coupled system where all you care about is the data that you worry about. That's it, right? Well, there will be, there will be a situation where, there's no way you can get away from it, get away from point-to-point calls, and you should not if you don't need MQ for some of the use cases we discussed earlier, but certainly MQ helps in the situation that you have presented. Okay, I think there's one more question. I'm just trying to go through this question right now. I think it's a question similar to the one that we had covered. So I'll just call out the question. It says, we are using decoupling in my application to make REST calls. The only challenge is, I think it's sort of a repetitive question, so I'll probably skip this. Okay, I think I have one more now. Let's go through this one. So this says I have 4 services, 1, 2, 3, and 4, which are taking each other through REST calls. In monolithic application, we can directly call required service as they're deployed in the same server as they are clubbed in single application, absolutely. In case of microservice architecture, as each component might deploy in different servers, we need to make a lot of HTTP calls. Which approach is most suitable in the case of better performance? We have discussed this in several principles we talked about today. You don't need to make a lot of point-to-point calls if you can leverage something like a message bus that we discussed earlier, right? So you could certainly have much more improved performance in terms of your local network traffic that you have to deal with if you leverage bus sort of infrastructure to be able to talk across components. That will certainly make your life much easier. One challenge I would mention though, with messaging to infrastructure is, besides the one I mentioned earlier about, clients keeping local copies without really needing them, is sensitivity of the data. So if you have data that's sensitive and you're dropping it on bus, you have to really make sure that your data is encrypted, or your out-of-the-box infrastructure for messaging queue, provides you encryption for data at rest, because otherwise you could be out of compliance. And that's very common use case in the payments and financial industry where, by requirement, by law, by compliance, you have to have encryption for data at rest. Otherwise, it's going to really break your back. Great. I think that pretty much wraps up all the questions that were presented to me. If there are any additional questions, I would encourage you to go to the TechGig website and post your comments. If I find additional questions coming over in the next few minutes, I'm going to note them down and put answers for those questions on the website. So thanks for being with me. I think you were a great audience with solid questions. And I'm going to look forward to do another session for you guys very soon. Thank you.
Thank you, Kapil. I'm really thankful to you for conducting this wonderful webinar. It was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of this webinar will be available on techgig.com very soon. Thank you, everyone. Have a great evening ahead.